Good morning. We're now recording. So what our plan is for today, I just realized it's got my border on here, so I'm just going to make some small adjustments. There we go. What the plan is for today is to finish up with tangent planes and differentiability, and then get into quadric surfaces, which is coming back to chapter 12 and picking up that section that we missed. Before I do that, though, I'm just going to pop over to another slide. And I've got here the midterm results. So I'm just going to quickly go through some of the main points on the midterm that I just wanted to address. Okay, sorry, I'm just a bunch of windows that need to get cleaned up. Okay, there we go. So what I like to do is I always like to give rough letter grade boundaries so that you can interpret your score with the appropriate confidence that I'm going to give you, because oftentimes we look at the numerical score out of the total and we work out a percentage, but we don't really know what that's going to translate to in terms of a letter grade. Let me just make the statement that grades in these courses that are for multiple programs, so such as Math251, it's a program requirement for many programs. These kinds of courses, we don't scale the grades in them. We can't scale the grades in them because there's a certain learning objective that's required for these courses in moving forward. And so, another way to say that, and this is the way I like to say it because it's a little bit more appropriate, is your grade in this course should not be dependent on anybody else's performance. It should only depend on your performance in the course. And that means that you can't scale the grades then, because as soon as you scale grades, you're forcing the grade that you get to be dependent on the performance of other people. And that's not what should be happening. Your grade, your letter grade that you receive, should be based upon your performance in the class and your performance alone. So having said that, posting things like this, the grade distribution, why am I doing that? It really doesn't have any effect on your grade, but what it does is it allows me to see how the class is performing and where the shifts have to be made, in the sense that I've got to reach a lot of people who are below the 50% area and get them up to speed. It's not, the boundaries aren't going to shift. The letter grade boundaries aren't going to shift to accommodate. It's the performance of the student has to shift up to get past those boundaries. Okay, so that's one of the reasons why I want to show this distribution is we've got some work on the bottom end there where we've got to get students maybe perhaps changing their study skills, changing their approach to the course in order to move them up. Okay, so the rough letter grade boundaries, if you were to just look at your numerical score and try to figure out what the letter grade that it would correspond to is, I've given you the rough breakdown over there. So 33 and up, that's an A. 27 to 33, if you scored in that range, then that's a B. 22 to 27, that'll be a C. If you scored just a little bit above 50%, then that's a D, and below 50% is an F. Okay, so I want to just go through and break down some of the questions. So question number 1, so these are the question by question distributions. So question number 1, it was done fairly well. There was a couple of parts that caused students to struggle with, but you can see there's a number of 100% there, and then there's sort of trails off there. The bulk is at sort of 70%. For this question. Some of the questions that caused a few problems was part E, true or false. Is that derivative equal to negative that cross product? The answer is true. Many of you started to do a calculation, but neglected at the end to realize that your cross product is in the opposite order of what's written here, so you have to switch the order. And when you switch the order to match what's here, you introduce that minus sign. I think there's a misinterpretation here. Those 33 to 40 is your raw score. So a raw score out of 40. So 33, if you received a grade of 33 or above, so 33 to 40, you got a rough grade, you got an A. Okay, how about question number 2? Again, quite well done. The problems that did arise were, you know, going ahead and finding the vector equation of the line that passes through a point and perpendicular to the plane. It was identifying what the direction of the line is. So the direction, if you're perpendicular to the plane, you can read off the direction the line is passing through, the direction the line is by reading off the normal vector to the plane. So this question was, we've got a parametrized equation of a line, we've got a plane written in standard form. Can you identify the pieces of it? Can you read off a point? Can you read off a direction from a line? Can you read off a normal vector for a plane? And so again, it was quite reasonably well done. There was a bunch of small errors that were being made, and some of them were just picking the wrong vectors, whether that was an understanding error or an error that was just made in haste. It's unknown, and that's sort of something you'd have to decide yourself as to how your error was made. As I haven't said, the solutions are posted. You can find the solutions on the assignments page of Canvas. You can also find them in the exam resources page, so have a look at those. This question, which was about the parametrized curve and doing a couple of things with it, finding a tangent line for one, that was part A, and just making sure that when you do parameterize your tangent line, you pick your parametrization so that the value which corresponds to 0 of the parameter is the point of tangency, and then as your parameter increases, you go off in the direction of the tangent line, and as it decreases, you go off in the opposite direction of the tangent line. So that one was fairly well done. Is the point on the curve? So that was checking to see if there was a value of the parameter t, that when you plug it into the curve r, you get that point 1 pi by 6 and 1. And then the last one was a antiderivative question. The most common mistake with the antiderivative question was just missing the constants of integration. You're integrating 3 components, and then you got to make sure each one of them satisfies the initial condition, or it's not an initial, but the condition that when you plug pi in, you get 1 out for each of the components. And that was the most common mistake, was just missing the constant of integration and then solving for it so that it passes through the particular point you want. This one was very nice to see. It was very well done, very well done. The limiting question, so determine whether this function has a limit or not, and we were stepped through it. Find the limiting values along the appropriate axes, and then what happens in the general case of a line of a particular slope m. So that was very nice to see. I'm quite happy with that one. These limits usually are the parts where the students find them the most challenging. So this was really nice to see that the question, which has historically been somewhat of a challenge on exams, was just nailed out of the ballpark by everyone. So really great job on this one. Question 5, this was meant to be a bit more of a thinker question, at least part A was. Part B was just a computation, do the cross product. So part A was explain why the direction had to be in the j-hat direction using orthogonality. So this was analogous to the homework assignment problem, one of the additional questions on the homework assignment. And it was just a slight change in some of the vectors there. And so the argument was to be the same, just slightly modified. So part A was meant to be the hardest question on the exam. And some people did quite well in terms of the explanations there. Part B was a component-based calculation. So just write down what I is and j is and an arbitrary a vector, and then do the calculation. All right. So what I'm just going to mention is that if you haven't got the solutions already, go ahead and grab the solutions. They are on the Canvas page, and you can double check your solution versus the solutions that I've provided. If you do have questions about the grading of your exam, you can pop into the workshop, talk with a TA about that. That's what they're there for. The workshop hours are a little bit limited this week, so it certainly can wait till next week. There's no rush in doing that. There's no deadline. Well, the end of the term, of course, but and the sooner the better. But if you don't get to it till next week or late next week, or actually next week is reading week, so it would be sort of the week following reading week or the week after that. Chat with a TA, get some feedback on it, and if there is really a concern and the TA identifies it, then there's a process for filling out a potential regrade form, and that's done through the regrading system. And so those are the best place to do that, because then they don't get lost. Emails don't get lost. There's all the automated queue there that I will then go and process. All right, let's carry on from where we were. We were just talking about differentiability of multivariable functions. So the definition of differentiability is that it's unlike the one in, oh yeah, go for it.
There's a couple comments in the chat.
Okay.
I'm wondering if you could just answer.
Attending workshop for marks? Nope. No, workshop is just a place where you can go and chat with TAs. Questions about marking of the midterm? Best option is to talk to the TAs in the workshop, but I'm also happy to chat as well. And so it can always be done after class, or if you want a private chat, then we can schedule a personal meeting. All right, I think I got all the questions. All right. So this tells us that differentiability of a multivariable function is really just meaning that the function can be approximated very closely by a plane at a given point. So is it differentiable at AB? Well, does it look like a plane if you zoom in close enough? And if it does, then it's differentiable. So that's what this definition is trying to capture. The nice thing, well, sorry, the not so nice thing about this definition is it's hard to apply. The nice thing about this definition is it leads to a theorem which is more easily done in practice to verify differentiability. And that's the theorem here that says if you have partial derivatives f sub x and f sub y near the point that are continuous, so if your partial derivatives are continuous, then the function's differentiable. So that provides a nice check for differentiability. You should just work out the partial derivatives. It's not whether they exist or not that determines their differentiability, but if they're continuous, then it's differentiable. So let's have a look at an example. So explain why the function f of x given here is differentiable at the point 3, 0. So the first thing we do is we work out the partial derivatives. And so the first partial with respect to x is given by that. And then the second partial, or the, I shouldn't say the second partial, the y partial is given by 2e to the 4y over the square root of x plus e to the 4y. So I'm just using the one-dimensional, or the calculus 1 chain rule here, and differentiating with respect to x in the first case, thinking of y as constant, and then in the second case, differentiating with respect to y, thinking of x as constant. And the thing to note is that both of these are continuous at 3, 0. Therefore, f is differentiable at 3, 0. So that means f is differentiable at 3, 0. It means that the tangent plane to the surface at that point is a good approximation to the surface. So that means we can go ahead and work out the tangent plane, or what we call the linearization in this case, if we're thinking of it as a function. The linearization is given by the function value at the point in question plus the partial derivatives in the two directions. So that's the x partial of 3, 0 times x minus 3 plus the y partial at 3, 0 times y minus 0. Okay, so that's essentially the tangent plane, but it's also, if we want to think of it as the linearization or the linear function that gives the points on the corresponding plane. So then at this point, we can go ahead and work out what these values are. F of 3, 0, so we plug 3, 0 in. That gives us the square root of 4 or 2. And then the x partial at 3, 0, that becomes a quarter just by plugging 3, 0 into the expression. It becomes an x minus 3. And then plugging in 3, 0 into the y partial derivative gives us a 2 over 2 or a 1, and then a y minus 0, so it just becomes y. So there is our linearization. So that's the function which gives a tangent plane at the point 3, 0. And so if this function is differentiable, which we verified it is by noting that the x and y partials are continuous, and therefore the function is differentiable, then this linear function is a good approximation to the function itself near the point 3, 0. So that means f of xy is approximately, actually, I don't even need to write f of xy because I'm interested in the particular case 3.1 and negative 0.1. That is approximately the corresponding value on the linearization. So that's what we get from differentiability, is the function is closely approximated by its tangent plane. And so the function value is closely approximated by the value of the linearization. And now we can just plug these numbers into the linearization, which is much easier to work out than the original function because it's a linear function. Linear functions are easier to work out values of. So I get 2 plus a quarter times 0.1, and then plus the y value, which is negative 0.1. And let me see, did I get these guys? Negatives, yep, okay, so just making sure I didn't make any sign errors. And then we can work out what this is if we want to sort of continue the calculation. So that's 2 plus 0.025 minus 0.1. I'm sort of running out of room here, but what is this? This is about a 1.9, and then so I'm getting well, maybe I'll do one more step here just to put in the last bit of details. So this is 2, and then minus 0. And I'm taking 0.25 away from 1, so that is going to be what? 0.25 removed from 1 is a 9.75, like that. You can verify my arithmetic here. And then we've got a 2 minus 9.75, and that's going to be a 1 point. So what are we? A 9.25. Oh, no, I'm getting it off here. So what are we at here? 2 minus something that's a little less than 1, so we're at about a 9.025, I think. Does that look right? Did I make any mistakes in there? I might have made a mistake. 1.025, yeah, it looks like we got that. Good. All right, so there is our linear approximation. All right. Let me just double check here. I'm thinking that we're a bit too far away, so I might have made a mistake. Let me see. Did I make a mistake here? You might be able to catch it. Oh yeah, there we go. I did make a mistake. Thank you. So where is our mistake? You're giving me the result? For some reason I can't see. I did make a mistake and I'm having a hard time see it right now.
It should be 2 minus 0.0975.
That's it. Thank you. And then this should be a, what are we at now? We're at a 9 and then a 2.5, I believe. Is that right?
Yeah, 1.925.
There we go. That's better. Okay, so the reason that I knew I had a mistake and I just couldn't see it, and this is often the case, the answer we know should be close to this value. It should be close to f of 3, 0, and f of 3, 0 is 2. So we know the number should be close to 2. And so we know that it should be 1 point something, or maybe something a little bit more than 2. And so my answer of 1.025, which I first had, that's far away from 2. That's too far to actually be an appropriate answer. Okay, so did I make that mistake just so that I could illustrate that point of checking your results? No, but it was a nice convenient thing to happen, because it does allow us to double check our results. If we don't get something that's close to the function value, then we know something probably went wrong. All right, so the next thing is the differential. Oh yeah, go for it.
I think 0.025 minus 0.1 should be 0.075 instead of 975.
Oh, did I get a 975? There we go. Yeah, that's better. And then that makes that answer, which I'm hiding behind my video. There we go. That looks better. Thanks. Thank you very much. And maybe you're wondering, is the other reason he did this so that when I say things like you can leave your answer in calculator ready form on the exam? That is a much more illustrative answer than the final numerical answer of 1.925 for grading purposes. This thing I've boxed in green shows us exactly how you worked out the value. It's not so much what the actual value is at the end. Of course, if you're doing this for a practical application, you'll want to know that end value. But for illustrating your knowledge, the thing I put in the green box is exactly the kinds of things we are looking for. Yep, you can leave it like that. Exactly, you can leave it like that, especially on exams. If you're asked to find linearization, boom, just leave it like that. Don't bother going ahead and doing the more tedious calculations of arithmetic, especially on an exams. Okay, so let's have a look at the differential. So the differential is just capturing the part of the linearization that's really the changing part. So we have that in our linearization at the very top. We have f of 3, 0 plus some amount of adjustment that the z values have to be moved by in order to get to where the function value is at that moved point, 3.1, negative 0.1. And so that little bit of movement is what we call the differential. And so that's what we've just captured here in this box, is that the differential dx is how much the z value is going to change by if you change the x and the y values by delta x and delta y. So here, delta x is essentially, it's the new x value. So maybe we'll call it, you know, I take my x plus and I move it a little bit, and then I take away my old x value that I started at. So that's what the delta x is, and then the delta y is, you move your y value a little bit, and you take it away from the original one, and that tells you how much you moved by. So that's what our delta x and our delta y are. There's just that h value that I've moved by. We also refer to them as dx and dy. There are independent variables which represent how much our x and y values have changed. And that tells us then that our z value, our differential, dz, is the partial derivative with respect to x times dx plus the partial derivative with respect to y times dy. So a direct analog of the differential for calculus 1. It's just that we got this extra little bit because we've got another direction to go in as well. So let's go ahead and find our differential for our function f here. The first thing we're going to do is work out the partial derivatives. The derivative with respect to x of sine is cosine, and then we also got our y partial, -3 sine y. Okay, so those are our x and our y partials, and now we can put them together to get our differential. Our differential dz is the x partial times dx plus the y partial times dy. Or in other words, it's 2 cos x dx plus -3 sine y dy. So there is our differential. And this is saying for this particular function, calculate the value f at pi by 2 and 0, and then use that to approximate the value at a nearby point. So the first thing we're going to do is work out pi by 2 and 0. So that's sine of pi by 2, which is 1, plus cos of 0, which is also 1. And so we have our value of 5. So at a very first step, we would say, oh, f of 29 pi by 60 and pi by 50, that's approximately 5. Because I just took a value that's close by and an input that's close by and worked out its value, which was easier. And so f of this other more difficult point to work out is approximately 5. But the differential allows us to adjust a little bit based on how the surface is behaving there. Is the surface increasing steeply in a particular direction? Use that. Use that to make a slight adjustment on how your approximation should behave. If the surface is really steep there, then as I move a little bit in a direction, then I should be able to say how high I have to move up, and that's what our differential is capturing. So what this is going to tell us is that 29 pi by 60, pi by 50, that thing is approximately the function value. So you might even notice that really what I'm doing is sort of a linearization here, but I'm just suppressing all of that extra bit about the derivatives in the linearization and just using the differential there. So this is approximately the function value plus the differential. And what is the differential? So the function value is 5. What's our differential? We can now work that out. That's going to be 2 cos of pi by 2 times dx. Dx is how far our input had to move. So we were at pi by 2 evaluating things. Now I want to know the value at 29 pi by 60. So I had to figure out how far did I have to move to get over to that value. And then -3 sine of 0. And then pi by 50. -0, but I don't need to write the -0 in. And so this is 0, and this is 0. So we get our approximation is 5. what the zeros mean for the partial derivatives is these tell us that the surface is horizontal at pi by 2 and 0. So at that point we took the tangent line at, the surface is horizontal there. So if I move over a little bit, then I'm still on this horizontal tangent plane, and that's a good approximation to the surface. So that's why I didn't have to increment anything, because I'm using the fact that it's a horizontal tangent plane there. Okay. This is a good summary. So point 15 here is a good summary of what we have for 2 variables, but it also applies for 3 variables as well. So I've written it here for 3 variables, but you can always suppress one of the variables and get a summary of what the section had in it. So there's a linear approximation. The function value of multiple variables is approximately given by the function at a particular point, plus the changes in each of the directions. So the x partial, y partial, z partial times their various changes. The increment in the output variable is just the difference of the function value at the new point minus the function value at the old point. And that is approximated by the differential. And the differential is just the partial derivatives coming into play there and how things have changed in each direction. So we can go ahead and work out an example that I've done a measurement of a rectangular box, measured the size, 80 centimeters, 60 centimeters, and 50 centimeters respectively. But there's a possible error in these measurements because I'm using a measuring tape or maybe I'm using some other form of measuring. Like I know the phones now, you can hold them up and you can get a good picture of an object, and it'll do a bit of augmented reality measuring of distances. Those, how accurate are those things? Well, in any kind of measurement you do, there's going to be a possible error. And so in this case, we're just assuming that the error is maybe a 1/5 of a centimeter. So in each dimension. And so what that tells us is that there's going to be an error in the volume that I compute. And so how big is the error in the volume if I use these numbers to compute the volume? So the first thing I do is I write down what our volume function is. It's dependent on these 3 variables, x, y, and z. And so what does that mean? It means that the error that I'm interested in, which is our delta v, is approximately given by our differential, dv. And our differential is given by the x partial times dx plus the y partial times dy plus the z partial times dz. And so that is yz dx plus xz dy plus xy dz. So that's what delta v is approximately equal to. That would be what our error is. So at most our error is yz times the magnitude of dx plus xz times the magnitude of dy plus xy times the magnitude of dz. So with an error, these dx, dys, dz's, an error of 2 centimeters means it could be either way. So what we have is that when x is equal to 80, y equal to 60, and z is equal to 50, we had errors where dx, dy, and dz are plus or minus 0.2. So they could be over estimates or underestimates. So there's this plus or minus part. And because of this plus or minus, that's where I use these absolute values. I just said, well, I'm interested in what the magnitude of the error is, and it's at most this. So now we can work these things out. So the magnitude of our error is at most y times z, which is 60 times 50 times 0.2, plus x times z, which is 80 times 50 times 0.2, plus x times y, 80 times 60 times 0.2. And we can work out the values of these things. I'll just jot it down. We get a value of 2,360 cubic centimeters. And so that is what our error would be in our volume measurement. If we return the volume as 80 times 60 times 50, then we could be as far away as 2,360 cubic centimeters from the actual volume based on these errors. So that's what these differentials are. One thing that they're useful for helping is error estimates. Error estimates and calculations where you use values that aren't quite accurate to compute some resulting value, and then you want to know, due to the inaccuracy of the initial values I started with, what is the possible error in my outcome? Are we supposed to calculate surface area? Use differentials, calculate. Oh, yes, you are. Okay, I'm going to change the question. There we go. Quick fix. Thanks for that. Yeah, for some reason I intended this to be a volume question, and I must have typed surface area when I wrote it out. But my intent was always for it to be a volume question. So the surface area was the mistake. So thanks for catching that.
Would the
All
surface
right.
area be a similar calculation?
Surface area would be, it's just you're going to have a bunch of terms. You're going to have, you've got your two sides that are the xy dimensions. So you'd have two of those. So it'd be like 2xy plus 2xz plus 2yz. And then you can go through and do the similar calculation. So the whole setup is pretty much the same. It's just your function is different. So for surface area, it would be 2xy plus 2xz plus 2yz. And then we'd go ahead and work out what delta S is. And so those would be the partial derivatives times the dx, dy, and dz. Okay, so let's have a look at this section now. So quadric surfaces and cylinders. So these are just coming back to chapter 12, and we're going to just look at some basic collections of surfaces that are going to come up now and again moving forward when we start talking about surfaces in space. So this is sort of like we want a catalog of surfaces that we just know something about in order to do examples with them later on. So for example, one of them is a plane. We've already dealt with these kinds of surfaces. So this is a plane, and the normal vector is 1, 2, 3. But what we're interested in this particular section is how to get a feel for what these things look like by taking slices of them, or what are called traces in appropriate directions. So if I want to look at what is the trace in the plane, let's say y is equal to k. So what that means is I'm going to imagine the surface drawn in space, and I'm going to cut it through the plane y equals k. And if I do that, then what I get is an x plus 2k plus 3z is equal to 4. And now that's just going to be a curve in this plane. So this is a curve, x and y, or x and z are our variables. And so we can see what that is. Maybe I'll solve for z. So I get a 1/3 4 minus 2k, and then I get a negative 1/3 x. So plus that. So this is our curve that we get just by rewriting that expression for z in terms of x. And this is a line in the plane y equals k. And we can get a slope. The slope is negative 1/3, and it's translated vertically. Depending on the k value, it's translated vertically. So what is this actually capturing? This trace is sort of capturing this idea where I've got I'll turn off my trace right now. I've got my plane, that's my surface, And all I'm doing is drawing a plane in the, well, parallel to the xz plane, so through a particular y value. And then as I let my y value change, what I'm going to do is stare at it from this side, is I get a line in this plane. I'm just looking at the intersection, and the intersection's a line, and its slope, in this case, is -1/3. You may say, well, it looks like it's positive. It's going up from left to right. Yes, but you have to remember that our x value is positive to the left now. So maybe an appropriate way to look at this is from the other direction, from behind. Now we can see it's going down. So it's a slope of -1/3. And all that's happening is, depending on the k value, the line is shifting up or down along the plane. And that's that vertical translation. And so we can get a visual that this is a plane just by seeing that, oh, it intersects this plane y equals k at a bunch of lines. And so gluing those lines all together then forms the plane. So we could do that for other surfaces as well. So in this particular case, we're going to look at z equals x squared plus y squared. And so I can do things like, what is the trace in plane z equals k? So when I draw a horizontal plane at height k, how does it intersect this surface? Well, that's going to be x squared plus y squared. I'm plugging in k for my z value. Gives me this, which is a circle with radius root k. So that means that at any given height, what I'm going to get is a circle. And in particular, I have to, since I'm taking the square root, I better make sure that k is bigger than or equal to 0, because it doesn't make sense when k is negative. There's going to be no solutions with a negative z value to this surface. There's going to be no points on it with a negative z value, because the z value is the sum of squares, which is always positive. So this tells me it's a circle. So what's happening here is, at a given height, I'm getting circles. And the circles are increasing in radius the farther I go up. And so I'm getting a shape that looks like this. And so we may think, well, how do I know how these circles are changing in radius as I go up? Well, I can look at traces in other planes as well. What's the trace in this case, I'll do the y equals 0 plane. So that's the xz plane. Well, when y is 0, I get z is equal to x squared, which is a parabola. And so I get a curve that looks like this. It's a parabola in the xz plane. And I can do the same thing in the other plane as well. I could do maybe a trace in yz plane. And that's going to be z is equal to y squared. Again, another parabola. And so that's this parabola here. And what we end up getting then is a pretty good drawing of what our shape is, just by looking at how it intersects various planes. So this is what this section's about, is getting an idea for what the shape of a graph is by looking how it intersects planes. This is what we call the paraboloid. In fact, what it's called is a circular paraboloid, because the circular part is the horizontal cross sections are circles, whereas these other cross sections are parabolas. So two cross sections or two planes, it intersects as parabolas. So it takes the attribute of a parabola, more dominant than the circle part, because the circle's only happening in one trace. But the circle part's happening in that one trace, so we call this a circular paraboloid, or just a paraboloid for short. Now, in the case where a variable is missing, we get what's called a circle, or sorry, a circle. you get what's called a cylinder. So a cylinder, here's our definition of a cylinder. It's just a surface that consists of lines called rulings that are parallel to a given line. So it's just a bunch of parallel lines that are all sort of stuck together, and that's what a cylinder is. The cylinder can be generated by a particular plane curve. So that's that red curve there that's drawn. And then we look at all these lines that pass through it that are parallel to each other, and that generates a surface called a cylinder. We can identify cylinders by having a variable that's missing in our equation of our surface. So here we've got that z is a missing variable. And so what does it mean when z is missing? So the trace in the plane z equals k is always the same. Because when I plug z equals k in, well, z's missing, so I'm not changing anything. It's always the same. It's always x squared plus y squared equals 4, which is a circle. So when I go and sketch the graph, I think, well, for any trace in a plane z equals k, so for any horizontal slice, it's always a circle. So we always have a shape that looks like this, all the way down. It's always circles all the way down and all the way up. And so what I get is what we typically refer to as a circular cylinder. Or, if you want to be more precise, a right circular cylinder. Though in grade school, you would have probably just referred to this as a cylinder, but now we've got a more general description for what a cylinder is. So this is one example of a cylinder, and it's a circular cylinder, but it's also the circles are stacked on top of one another, or in other words, there's a right angle between the circular cross-section and the side, so we call it a right circular cylinder. How about this one, y equals z squared? Well then, we've got the z, or the x variable missing, so the trace in plane x equals k is always the same. And it is a parabola. So that means if I go to sketch this thing, it's going to consist of parabolas along the y-axis that are in the parallel to the YZ plane. So we're going to have things that look like this. There's a parabola. And I'll try to see if I can get a good sketch of this. So here's another parabola cross section, and so on. Maybe I'll do another one up here. Another parabola cross section. So it looks something like that. And now I'll draw the top line of our parabola. So something like that. It's our parabola, a cylinder made up of parabolas that are traveling along the x-axis. Okay, so those are cylinders. Quadric surfaces are the analog of conic sections. So these quadric surfaces are given by equations in x, y, and z, where the highest power on them is a 2. So they're polynomials in x, y, and z, and the highest power is a 2. And they can be put in one of these standard forms. Yeah, we also have non-circular cylinders. You can just take an ellipse and stack it up. Or this one's a non-circular cylinder. This is a parabolic cylinder. Maybe I could write that in here. This is a parabolic cylinder. It's made by taking that shape of a parabola and just pushing it in the different directions to maybe like a bubble wand, if you want to think of it that way. I'm just taking this thing and I'm moving it along a particular direction, and it traces out what's called a cylinder. So quadric surfaces are basically equations in x, y, and z where you've got at most a square on it. So I'm just going to do a couple of examples really quickly because they're familiar to us already, and then we'll call it a day. So this one, we already know what it is. It's a sphere. So that's an example of a quadric surface. It's a sphere. How do we get it through traces if we wanted to do a trace approach? Well, I'm just going to take traces in the vertical direction. So what does it look like when I slice it at a particular z height? Well, I get an x squared plus y squared is equal to 4 minus k squared. And in order for this to make sense, I have to say, well, k can't be any smaller than -2 and any bigger than 2. Because as soon as k gets too big, 4 minus k squared becomes negative, and x squared plus y squared is positive. So you'll never get solutions there. So k is trapped between these two values. This is a circle, and the radius is the square root of 4 minus k squared. So what we have is that we have circles stacked on top of each other in the z direction. The biggest one occurs when k is 0. So that's at height 0. And we can go all the way up here to a height 2, all the way down here to a -2. And in between those values, the circle's just shrinking. So it's going to look something like this, where at various heights, we just get smaller circles. And so there's a drawing of our sphere that uses traces. The last one, just so you have another example, one that we haven't, well, we've seen it before, but we'll do it again using traces. So we'll go traces in plane y equals k. So this would be x squared plus z squared is equal to k. These are circles. But we could also go trace in plane, maybe I'll say x is equal to 0. That would be a y equals x squared. That's a parabola. Or I could do the trace in plane z equals 0. That's y equals, oh, sorry, that first one was that one's a z squared. Sorry, in this case, it's an x squared because the z value is 0. That's again a parabola. So I can take that information and build it all into my picture. As I move along the y direction, I get circles. And they're shrinking as I get closer to the origin. But if I look along the x equals 0 plane, I get this parabola. And if I look along the z equals 0 plane, so the horizontal plane, I also get a parabola. And so what I end up getting in the end is a paraboloid. Again, and it's a circular paraboloid because the cross sections in the direction it opens in are circles. You'll see in the examples in the textbook, they get elliptical paraboloids because they make some changes where the first trace is ellipses. All right, so we will wrap up the last two examples next day and then get on to curves again and looking at arc length and curvature. So I'm just going to